Thank you for joining Solmax today for our third webinar series. Today we'll be talking about enhancing containment quality assurance with the help of conductive geomembranes. My name is Doyen Adesokan, and I'm a technical manager at Solmax. I've worked previously at Tetra Tech EBA and at SNC Lavalin in Canada. I have a bachelor's in mining engineering and a master's in environmental engineering and environment and sustainability. And I'm completing a PhD in the area of sustainable geotechnics, assessing the performance-related properties of tire-derived aggregates, which is shredded tires, for use in engineering applications as a substitute for gravel. And I'm currently registered in Saskatchewan with APEX. An outline of what we'll be talking about today, I'll talk about what quality assurance and containment is, the types of defects that are out there and why we should care, the avenues for those defects and how to prevent leaks, the leak location methods that are available, and Solmax's conductive geomembrane. I'll describe how it's made, how it's installed, and how it's leak tested. So in quality assurance, when it comes to containment, we're basically looking for defects in the welds and defects in the geomembrane panels that could result in leaks. The picture on the bottom, the right one, is a picture of a defect or a hole that was found in the weld during the leak location and quality assurance survey. And then the picture at the bottom left is a picture that was found on the geomembrane following a leak location survey as well. For defects in the weld, there are quality control measures that are taken to ensure that the weld is of good quality. So we perform the peel test and the strength test. In addition to those quality checks, we also perform leak location tests on the weld. And for this, we do the air channel testing, or the spark testing, or the vacuum box testing. In addition to the welding test, or the check for defects in the welds following installation, we also check the geomembrane panels itself to make sure there are no holes that can cause leaks. And there are several methods out there for doing this survey, and I will be talking about these methods in the webinar today. What are the types of defects out there? There are fully penetrating defects, and these are defects that go through one end of the geomembrane through the entire thickness and come out through the other end. So anything from pinholes to holes or cracks or tears. And then there are partially penetrating defects. These don't go through the entire thickness; they just go midway or a few ways into the thickness of the geomembrane. And there's something called, or which I have grouped as, latent defects. So these are defects that we can't really see, but they're there. And then given the right condition or combination of conditions, they might become fully penetrating defects or significant defects that can generate leaks. One big example is wrinkles. Now, wrinkles in polymeric geomembrane is a big concern. When geomembranes are exposed to direct sunlight, UV radiation, they expand and contract, and this expansion and contraction process generates wrinkles and folds along the geomembrane panels. And there's so many issues associated with wrinkles. The first thing is, what has been found in the literature is wrinkles don't go away even after backfilling. What happens is they fold over, and the peak of the wrinkle and the bottom of the wrinkle become tense or localized. They undergo localized strains, and these are areas for defects. So they're areas of weakness, and they're areas for potential defects in the geomembrane with time. Another thing with wrinkle is it reduces the contact between the geomembrane and the subgrade, and what we found is that using the Rowe's equation for calculating leaks through a composite system or a composite geomembrane, holes on wrinkles can cause about 10 to 10,000 or 1,000 more leakage than when there is intimate contact between the geomembrane and the subgrade. Another issue with wrinkles is it can result in poor quality welds because it makes it more cumbersome to do the welding when there's lots of wrinkles, and this can generate poor quality welds as well. A third or another latent defect is localized strain. So at the anchors of the geomembrane, there could be localized strain with time. and this can result in defects over time. So why should we care about finding leaks? The first thing is respect for the environment. So we always talk about protecting the environment, protecting groundwater, protecting land. But then taking this a step further is to just be concerned about how our activities affect the environment. And there's so many people, or the people whose livelihood depend on these resources like groundwater and land. So we need to find those leaks so that we don't contaminate the environment. Another thing is responsible operation. So nobody wants to be, or nobody I would expect should want to be that company that pollutes the environment or has a reputation for causing contamination into the environment. Another thing I found is if it can be shown that there is a consideration, or there's a proposal, or there is a plan to perform leak location surveys on the containment facility, this might go a long way in aiding permits for certain applications. Another reason why we should find leaks is regulations and fines. So there are regulations out there for zero leakage, and there are regulations out there for allowable leakage rates. And all of these have repercussion, and they have liabilities attached to them if they are not adhered to. Another reason is rewards. And I'll use an example of a heap leach mine in this instance, where a low-grade ore is mined by heap leaching. At the base of the heap leach pad, there is an impermeable barrier system, and the purpose of this is to achieve maximum recovery. So we don't want the miners don't want the ores to get out into the environment, and we don't want them to lose the minerals as well. So we have to find leaks in this instance. Another reason is the chemicals used for those heap leaching are highly they might be in high concentrations, and we don't want these materials to get into the environment as well. So those are two reasons why, in this instance, it's rewarding to find leaks. The geotechnical issues include if a leak happens to be on a slope, there's a chance of progressive erosion of that slope with time, which could result in slope instability. And another reason is even if it's not on a slope, if it's just on a flat base, and the water is retained, say, under a wrinkle over time, studies have shown that there's a potential for rapid oxidation of the geomembrane from that fluid that's retained at the bottom of the geomembrane. So there's a need for us to find those leaks and have them repaired so as to extend the lifespan of the geomembrane. So there's several avenues for holes in geomembranes. I'll do a cradle-to-grave evaluation here. I'll start from manufacturing, which is the cradle. The manufacturing, I would say, doesn't generate so much holes or defects in the geomembrane because the industry standard is highly stringent. And over and above what the industry has set for us, at Solmax, we have a zero leak policy for all of the geomembranes leaving our plant. All of our geomembranes are spark tested during production for holes, and any material that doesn't meet our quality control process is pulled out of the process, pulled out of circulation and discarded. So you can rest assured that any material that you're getting from Solmax has been leak tested rigorously. Transportation as well, that's another source for defects in geomembranes. What we do with Solmax to ensure that all of our carefully manufactured materials are delivered in good condition to the site is, in all of the shipping containers, we ensure that the floors are free of debris or anything that can cause physical damage to the geomembrane. And in addition to that, we put a sacrificial layer of geomembrane at the bottom of the shipping container to ensure that there is no physical damage to the geomembrane. And also with all of the materials that we supply, we'll have a list of a guideline on how to deploy the material, how to store it, how to load and unload to prevent any physical damage to the geomembrane. Installation is a big one when it comes to holes in geomembranes. It was found in a study a few years ago, or by Nsoko, that 24% of holes in geomembranes were from installation in that study. And a huge percentage of those holes was from poor quality welds. And then there was another high percentage from poor welding, so burning of the geomembrane from too high or too high a temperature or too slow a welding rate. And then there were also instances of stone penetration as well, so overlying material, underlying material, and then there were cuts during the installation. So all of this accounted for 24% of holes that were found during the survey in the geomembrane. Also in the same study, they showed that 73% of all the holes they found were from placement of cover material. So things like stone puncture accounted for the highest percentage of all of the 73%. And then there was heavy equipment damage, which was like 16%. I'll say at this stage that the industry has changed and the practices have changed a little bit. So what we find more now is fewer holes during backfilling. However, they're larger in diameter. So we find more of the smaller diameter holes following installation, and then we find fewer of those large size holes following backfill. So how do we prevent these holes and all those leaks and damages to the geomembrane? The first thing is the stringent manufacturer's quality control is required. Spark testing during manufacturing and ensuring that the material is transported to site with sufficient and adequate care to prevent any damage. And another thing is during installation, thorough quality control is required. So checking of the welds to ensure the welds have good quality, performing the welds as per standards, using the right temperature and the speed, taking extra care to prevent accidental damage to the geomembranes during installation, checking the welds for leaks, using all the methods I mentioned earlier. This can go a long way in preventing leaks. Another main one is the design of the system in the first instance. So a double barrier system is going to go a longer way in reducing leaks than a single barrier system. Also, specifying good quality products, materials that have high long-term performance. So products that have a high stress crack resistance or a high puncture resistance, or products that can minimize wrinkles, like a material with a white reflective surface. And another thing is careful backfilling as well. Having said all that, sometimes, despite of what we do, or regardless of whatever strategies we put in place, we may be able to implement all of the strategies carefully, and sometimes we're not able to implement all of them, and leaks just happen, regardless of what we do sometimes. And there's something we can do about it. We can deploy electrical, or not just electrical, we can deploy leak location methods to the site to find those leaks and have them repaired before they compromise containment. So how do we go about finding all those leaks? There are several methods available. The electric leak location method, the acoustic method, and the infrared thermographic method. The electric leak location method involves measuring current flow through a geomembrane, and the current will only flow if there's a leak in the system, if there's a leak in the geomembrane. The acoustic method utilizes some special microphones, and they can detect the noise of water or the flow of air through a hole. The infrared thermography method is for uncovered geomembranes, and it's been reported on the sites that offer the services that they can detect latent and partially penetrating defects. So electric leak location is the major one that's out there, and there are two kinds. The ones performed on the geomembrane when it's still bare are the water puddle method, which is also known as the water lance method. The only difference is the flow of water or the volume of water used. There's an arc testing method. There's a spark testing method, which is performed on a conductive backfill membrane. And then for the ones that are done after the backfill material has been placed on the geomembrane, we have the dipole testing. And the dipole testing can be performed if there's water, if the covering material is water, or the covering material is a conductive solid material. The water puddle test involves spraying water onto the surface of the geomembrane through a water lens device, and then applying direct voltage to that water to charge up to create a conductive surface over the geomembrane. And then if there's a leak in the system, the current flows from the water through a conductive subgrade to a grounding electrode that's just outside of the geomembrane area. And here is a picture of a technician performing a water puddle test. You can see the water coming out from the water lens device, sprays the surface as the surveys, and it just progresses and surveys the whole area. And once a signal is detected, they can narrow down on that signal and find out where that leak is and have it repaired. The water puddle test has a few advantages, and it has some limitations as well. The first advantage is it's effective on geomembranes that are not covered, and you don't need a conductive backing to perform this test. And it can detect pinholes, so 1 millimeter diameter holes can be detected. And it's very good if the surface is flat or if you have a gentle slope. A few limitations include you need a water source to perform this test. So if water isn't available, you may not be able to utilize this method. And also, moving the water, having a storage tank, or moving the water around might require an extra assistance. So all of that might add to the cost of the project. If you're working on a vertical surface on a steep slope, it may not be effective because the water is just going to trickle down the slope. And it may not detect holes and wrinkles. You may have to flood or fill up the wrinkles with water and create like a hydraulic connection between all of the wrinkles to be able to detect holes and wrinkles. So intimate contact between the geomembrane and the subgrade is required for this test. And because we're relying on the conductivity of the subgrade to transfer current when there's a leak in the system, if the subgrade isn't conductive, the test we won't be able to perform the test. The second test that is performed on uncovered geomembrane is the arc testing. And this is pretty similar to the water puddle method or the water lens method. But instead of water here, we're not spraying water onto the geomembrane. We're applying direct current or voltage to the test wand, and then we're moving that wand across the surface of the geomembrane. If there's a leak in the geomembrane, then there's a signal, there's an arc that's created across that leak, and current flows from the leak through the conductive subgrade to the grounding electrode, and then sends the signal to the technician. A few advantages of the arc testing method is there is no water required, and it's effective on uncovered geomembranes. It can detect holes, pinholes as small as 1 millimeter diameter, and it's very effective on vertical surfaces or steep slopes. A few limitation is if there are wrinkles in the system, again, because we're relying on the conductive subgrade, it may not detect that wrinkle. And if the surface is not clean or dry, it may not work effectively as well. The spark testing method is the third method for uncovered geomembrane, and this is different from the other methods. In this instance, we don't need a conductive subgrade. The conductivity of that we're using for the test is from the bottom layer of the geomembrane. So we need a conductive backing under the geomembrane for this to work. And because we're trying to, so we apply direct voltage to the surface of the geomembrane, and we require very high voltage, about 35,000 volts, because we're trying to get the current to spark through an insulating layer of geomembrane to go through the conductive layer. And that's why we use a very high voltage. So we apply the voltage to the test wand, and we survey the area. And if there's a leak in the system, we get a spark, and then we hear an audible beep. And then we can then narrow down on that leak and make sure it's a true leak and have it repaired. Some of the advantages of the spark testing is it's effective for detecting pinholes, just like the other methods. And it has an extra advantage it has over the other method is it's effective on detecting holes and wrinkles. So with the spark testing method, we can say that wrinkles become virtually invisible because it can detect that hole. It's effective on slopes and on vertical surfaces, and subgrade conductivity is not required because we have the conductivity from the geomembrane itself. Another advantage is we don't have, we have the grounding electrode just right behind the technician, so we don't have long wires just connected outside of the geomembrane, which could be a little bit cumbersome as well. It has limitations. A conductive backing is required to perform the test, and the surface must be clean and dry. And there are limitations with if the testing or the detector isn't calibrated properly, there might be issues with sensitivity. So there might be issues with false positives where there are no leaks, and it's just a matter of calibrating the device properly. So getting the sensitivity right. If it's too sensitive, then we get false positives everywhere. If it's not calibrated properly and the sensitivity is too low, then we miss all the tiny holes. So getting that calibration correctly is one of the limitations with this process. The dipole testing is a test that's performed when a geomembrane is covered with, say, water or a conductive solid material or earth material. And in this test, we're applying the voltage to the cover material, and we're relying on the geoelectric properties of the cover material and the soil, the subgrade material, to transfer current if there's a leak in the system. So in this case, we can't really see an arc or see a spark or hear a beep because we're working on the geomembrane that's under like a meter or less of soil. So what the technician will rely on in this case is a distinct sine wave. So at the bottom there's a graph there that shows the sine wave. That's what the technician is looking for. When he gets that signal, he knows there's a leak somewhere, and they can narrow down on that signal and find exactly where that leak is and excavate and have the leak repaired. A few requirements for performing dipole testing is the cover material has to be isolated in the area, and then the thickness of the cover material as well is essential, and it's recommended to keep it at about 0.3 meters. That's about 12 inches. And another consideration is a homogeneous cover layer is required. So if the plan is to have like 4 layers of cover material over the geomembrane, eventually it's best to perform the leak detection where you have the first layer of material. Say if you plan to have sand, gravel, or sand geotextile or other layers, perform the leak detection when the first layer of material is on the geomembrane to achieve an effective leak location process. And here is a picture of the dipole testing. The dipole testing is performed in grids. So the technician moves that equipment around the survey area in grids, and they look for that sine wave signal. There are a few advantages of the dipole method. When the cover material is soil, the dipole method can detect up to 6.4 millimeter diameter holes under a cover material of about 2 feet, 0.6 meters. A few limitation is when the condition isn't right, say the top or the bottom layers are frozen or not conductive, then we may not be able to perform this test. And also the leak sensitivity or the detection sensitivity decreases as the thickness of the cover material increases. And if there are holes and wrinkles, the conductive, unless a conductive backing is used, the dipole method may not detect those holes on the wrinkles. And in the double barrier system, where you have a primary geomembrane, a secondary geomembrane, and a leak location layer in between, if there's a leak in the primary geomembrane, there may be need to flood the system to detect leaks unless a conductive conductive backed material is used. So it could be a geomembrane. Now, the dipole method on the water, when water is the cover material, has a few advantages as well. It can locate smaller diameter holes than when soil is the cover material, and it's more sensitive than the water puddle or the water lens test because the head of the water is higher. So this pushes down the geomembrane and creates a better contact between the geomembrane and the subgrade material. A limitation is if the water is saline, then the conductivity gets too high, and it may be a little bit complicated for just the normal dipole method, and other advanced testing may be required. So a few recommendations now. So which one do we perform? Do we do leak location before backfilling or after backfilling? The recommendation is to perform both. Do a leak location following installation to find all those tiny or smaller diameter numerous leaks, and then do another one following backfill to find the fewer larger diameter leaks. It's understandable that in some instances, there may not be enough, the budget may not cover both of the methods, and we can only do one. So which one do we go with? The dipole method is recommended. It's a matter of opinion, but however, it's a good recommendation. And the reason for recommending the dipole is the bigger diameter leaks. Those are the significant. Those could be the significant ones in the containment facility. And another reason for performing dipole is the latent defects or the partially penetrating ones might become fully penetrating following the placement of backfill. And the picture on the right is an example of that happening. The weld, there was a poor quality weld, which was missed during the quality control process on the uncovered geomembrane. And then following backfilling, the weld came open and became a leak. So if dipole hadn't been performed, they would have missed that defect or that source of leak in the system. Again, to back up the recommendation for leak location, here is a summary of a study or a statistical analysis that was performed by Beck 2012, and it was delivered in a conference in a while ago. And what they found, or what they arrived at, was the probability of exceeding an allowable leakage rate that is astringent, at say 5 gallons per acre per day, decreases when the combination of leak location methods increases, or when a combination of leak location methods are used. Now, I'll describe, or I'll talk about allowable leakage rate for a second here. Allowable leakage rate or action leakage rate is not a permission to leak or discharge materials into the environment. This is only applicable to a double barrier system where we have a leak location layer between the primary geomembrane and secondary geomembrane. So the allowable leakage rate is a specified, or the maximum leakage that has been specified for that leak location layer. When you have a single barrier system, it's an absolute zero leakage into the environment. So what Beck 2012 found was when leak location is performed on an uncovered geomembrane following installation, the probability of exceeding that stringent 5 gallons per acre per day leakage rate is about 69%. When you perform just dipole, then the probability decreases to 51%. Now, when you combine a leak location following installation with dipole after backfilling, you drop that probability to about 12%. When you perform leak location in an uncovered geomembrane, white geomembrane, where the wrinkles are decreased and you have better intimate contact with the subgrade, and then you follow that up with a dipole test after backfilling, the probability of exceeding your leakage rate drops to about 1%. Now, when you perform a leak location on an uncovered conductive back geomembrane, and you follow that up with a dipole test following placement of cover material, the possibility or the probability of achieving your leakage rate or exceeding your leakage rate drops to 0. So this clearly shows that it's possible to have a leak-free containment facility, but we just need to know how to combine those methods, the available methods, effectively. So now I'll talk about Solmax's conductive back geomembrane, and here is a picture of spark testing being done and the distinct spark that comes out when the survey area or the survey wand goes over a leak. How do we make the conductive layer of our geomembranes? We use carbon black. Carbon black is added to polyethylene geomembranes because polyethylene is susceptible to ultralight UV light degradation when exposed to sunlight. So carbon black is added so that it can absorb all of that UV light and prevent the UV light from attacking the polymer chains to prevent degradation. Now, carbon black is conductive on its own, and the actual conductivity depends on how you manipulate the structure of the carbon black, the particle size, and the loading level of the carbon black in the production process. At Solmax, the way we produce our geomembrane is we use a three-layer core extrusion process. So we have a core layer that has all the mechanical properties of the geomembrane, the same, and then we have the top and the bottom surface finishes, which we can change depending on what the client or the application requires. So for all of our products, say HDP, the core materials are the same, but then the surface finishes can be changed. So for the conductive layer, what we've done is we've taken the core, the surface, one of the two finishes, and we've added the carbon black to that layer to make it electrically conductive. So about 3 millimeters of the core extruded finish is electrically conductive carbon black. And the conductive layer can be applied to most of our products, our HDP or LLDP standard or premium products. The conductive layer can be spark tested, as I described earlier, following installation, and it can be dipole tested following backfilling as well. And here is a further description of the equipment we use for the spark testing. You can see the neoprene pad, the grounding pad. So we don't use a grounding electrode in this instance. We use a neoprene pad that's connected to a holiday detector. I think the name is holiday detector because it's supposed to detect play in the system. So the holiday detector applies high voltage, about 35,000 volts, to the neoprene pod and to the test wand to charge up the geomembrane. And then as we survey the area, if there's a leak in the system, we see a spark and we hear that sound. I'm going to show you a video of what that looks like now. Just a quick video. Okay. So that's the spark and the beep that we hear. So it's highly effective. So you see it as you go. So how do we install the conductive geomembrane? The first thing is to even recognize which side is conductive. We try to make this easily recognizable. It's the outside side surface of the roll that we supply, and it's the opposite side of the printing line. If all of these indicators are missing for any reason, then you can just use a multimeter to check and see what side gives the signal and what side doesn't. And once you know what that side is, just put a label on that side and ensure during installation that's the side that touches the subgrade. And then for the welding, what we found is we don't need a specific welding equipment to weld a conductive geomembrane. And what we found again is that you may have to slow down a little bit more than, you may slow down a little bit more, about 20% less speed than you would apply if you were welding a regular geomembrane, say a regular HDPE. If you were welding a conductive HDPE of the same thickness, you may have to slow down a little bit more and apply more pressure. And this is just so you can break the conductive layer across the seam and ensure you have enough squeeze out of the conductive material. And you can use a double channel welding machine for the seam. And if there's a patch or it needs to fix a defect or a leak, you can just use the regular extrusion welding methods as well. And another thing is to calibrate the welding machine appropriately. So perform trial welds to know the exact speed you need and the pressure. And once you've performed the seaming, you can use a multimeter again to check the adjacent panels to make sure the conductivity is broken across the films. Once you get the parameters right, then you can deploy that setting on the field. Just to say, installing any conductive geomembrane, not just Solmax's, requires special installation and welding procedures. And it is for this reason why when you buy any product from us, a conductive material Solmax will give you free training on how to install this material, on how to perform the leak location surveys following installation and following backfilling. I'll give a recommendation here again. When you place an order for Solmax's conductive bacterial membrane, you can have the surface finish in white. And I showed the statistics earlier on how the white reflective surface, when combined with a dipole, decreases the leakage rate by about 90%. So we can have the top layer with a white finish and have the bottom layer as a conductive layer. So you get the benefits of you get two benefits in one. And in addition to reducing wrinkles, another benefit of the top white layer is defects are easily identifiable. We scratched a line into the white. If you see the picture on the right, there's a line that we drew into the white geomembrane, and we scratched the same line into the black geomembrane. You can't really see that line in the black, but it's very visible even from where I'm sitting. I can see that line there. So that makes quality control quicker as well. So the benefits of Solmax's conductive geomembrane, to recap and tie it all together now, is it can be spark tested to detect pinholes as small as 1 millimeter diameter. And a good thing is intimate contact is not required because the spark testing can work even when it can work on holes and wrinkles, because we're not relying on the conductive subgrade. We're using the conductive layer at the bottom of the geomembrane. It's highly effective on slopes and on vertical surfaces. And again, yeah, like I mentioned already, the subgrade conductivity is not required. Another benefit for the dipole test is in a double barrier system, there is no need to flood the leak location layer when a conductive back material or like a geomembrane is used. And also in just regular areas, there's no need to flood the wrinkles to be able to detect holes and wrinkles. You don't really need intimate contact between the geomembrane and the subgrade material. And not having to flood and use water-based methods can save some money as well, and the time associated with flooding, say, a leak detection layer and having to drain that layer and having to dispose of the water. I read in a study where they had to flood the leak location layer, and it took about 2 weeks to drain that layer before they can continue operations on the site. Another one I found is in some areas, they specify 3-layer double barrier systems. If we have, and all of this is just to prevent leaks, so 2 is good, 3 should be better, right? But if we have a conductive bacterial membrane, from all of the description and benefits I've described already, there may not be a need for a 3rd-layer barrier system, and this will save a lot of money in the project. So in conclusion now, the conductive geomembrane that we're offering as Solmax is a smart way of achieving high performance in containment. So it's a cost-effective way of ensuring that a containment facility does what it's supposed to do, which is to hold on or retain materials. And although we can train an installer to perform the leak location test, it's recommended or it's advisable to retain the services of a third-party leak location company to do the test, just to avoid conflict of interest and to gain from the experience as well. And to conclude, I would say that at Solmax, we're more than just a manufacturer of geomembranes. We're providing solutions for maximum performance at the best available price. And on that note, I'd like to say a big thank you to Group Alphard for the support, and we'll take questions now. Thank you.